Know about everything. Yeah, so coredumps. One of the privileges, or I don't know if it's a privilege of kernel development, is that from time to time you get to open a file and be reminded that A, it exists, and B, that it's terrible. And then the question is, what are you going to do about it? Close it and like ignore it, or try and change it a bit? So one thing that I did this year was like I not just massaged that code quite heavily. I also changed how you can do coredumps in the kernel, and this is something I've discussed with Leonard and a bunch of others, because like systemd is one of the main consumers of this. And the thing that pushed me over the edge to actually do it was the new slew of CVEs that we had. There was like a couple of them related to coredump handling, because it's apparently pretty easy to generate CVEs, especially when setuid binaries are involved, because they are bad, as you might have already heard from Leonard a couple of times today. So brief reminder, what is a coredump? It's when a process crashes, a snapshot of its memory contents and metadata is generated by the kernel, and then it's made available to userspace. It can be triggered by a bunch of different signals, and the coredump is generated in ELF format, probably a historical artifact. ELF header, program headers, sections containing process metadata, and then the memory contents, which is probably what most of you are most interested in. And it obviously allows you to do post-mortem analysis when your process unexpectedly crashes. So it's quite valuable. I don't know, how many of you have dealt with coredumps over the years? Okay, this is basically everyone. Was it a great experience? There are different coredump modes. It's an atrocious API with endless historical wards and pretty weird behavior. Like one of the things that I'm not a big fan of procfs. Like it's fine for reading reading metadata about processes and so on, but especially for configuring security-sensitive stuff like coredumps and so on, I've always found it a strange design decision. The same thing with, like you heard it before in Leonard's talk, people who were there here, like UID map and GID map, that you suddenly configure user namespaces through procfs. I find it all very weird, but okay, it's a historical thing. One can understand why people did it this way originally. So there are a couple of files, procsys kernel core pattern, that's probably the main file for how how coredumps are generated. We'll touch on that in a second. And then we have core mode and the coredump filter, where coredump filter is like, what you can do is essentially exclude specific memory contents or memory regions when a process dumps core, which again, I think is also a weird API, because like when you start a process, you then have to set a coredump filter for this specific process at the time when that process is started. And not at the time when the coredump is generated when you would actually like to do it, which is also kind of weird, I think. So the oldest coredump mode. By the way, I copied a bit of the code on the right side. I don't know how well you can read this. I thought this would be bigger, but okay. Anyway, huh? Not at all. That's great. It's basically just the file. Everything that you need to know about coredumps is in a single file in the kernel, fscoredump.c, and I've cleaned it up so all of the different modes now have separate functions in which they live. And the oldest mode is simply instruct the kernel to write the coredump somewhere on disk, right, on the file system. It means the kernel literally creates a file, opens it, truncates it, and then dumps the coredump in there, which obviously means if you have a setuid binary, for example, the kernel runs around with like root privileges and writes a coredump for you. So you can already see this is probably not a good idea. And you can parameterize it. You can pass additional, like for example, you can say append the PID to the name. You can use relative paths. You can use an absolute path. And so you can at least ensure that the name is unique for the, well, somewhat unique for the coredump. But this is largely legacy. I would assume that mostly this is done on embedded devices. I don't know if people actually use this in real life extensively. It seems like a very bad idea in general to do this. Yeah, so this is the oldest mode, but I'm pretty sure Actually, who is familiar with the Coredump API in general? Okay, Martin for sure. Yeah, a bunch of you. Okay, and then someone, not someone, I know who it is, but in the 2 dot something kernel releases, somebody came up with the idea, okay, this is probably not great how we're currently doing it. We need more flexibility, and we want user space to be able to process coredumps more individually or better. And so this is where the most common way of generating coredumps come in. And this is the user mode helper. We get to that in a second, and you can see that like this little pipe symbol, what you see right here, systemd-coredump, that string, that's what would be in proc sys kernel core pattern. And the little pipe symbol at the beginning, that instructs the kernel to use a user mode helper. Who knows what a user mode helper is? Okay, a few, that's already good. It's terrible. It's one of the original sins. It's basically the kernel spawns a thread for user space, but it does it from a system work queue. So the kernel obviously maintains threads himself. Like for example, for stuff like write back means you have a page cache, right? And so when a write goes to the kernel dumps it into the page cache. It doesn't immediately write it back to the file system. So at some point, the kernel will start a write-back thread, and that's essentially a separate worker in the kernel that's maintained by the kernel. And we have the system, for example, system work queue, and the system work queue also does other stuff, like you can punt work into there that you need to do asynchronously or can do asynchronously, and the kernel just gets to it when it gets to it. Like different modes how you can use this, but that's the general idea. It's an offload mechanism. And what you can also do is you can use a user mode helper, which means the kernel forks, it literally forks, and then XX from the system work queue. And like if you're a bit familiar with how this works, you can probably already guess what this means. You start with like full kernel privileges. Like, I mean, you fork an exec in the kernel, so that means the user mode helper that gets invoked starts with full level kernel privileges. Every capability you run around on the file system, like super privileged. So if you manage to somehow corrupt this user mode helper, you're fucked. We use it in a couple of locations. It's not that common anymore. I think 2 or 3 years ago, we added a new concept which is called a user worker. So I did some work to it's essentially how user mode helpers you would want user mode helpers to have been done, and it's also how IOUring worked. Like IOUring originally also used kernel level threads. And that turned out to be a horrible idea because, again, you need to make sure that you run with appropriate credentials and not constantly with kernel-level credentials. And if you fuck this up only once, you have a problem. And so what you can do now is that the kernel can spawn processes for user space, but it does so with the privileges of the processes that requested it. So the kernel essentially forks a new process for the requesting user space process, and the thread becomes a child of the user space process, because another consequence of using the user mode helper is you don't inherit C group settings, you don't inherit R limit settings, anything at all. Like it means you're not bound by any of the restrictions that the parent that triggered the user mode helper creation was subject to, especially like C groups, like no memory limits, nothing, like unbounded. Which also means that if you are spawned as a user mode helper process like systemd-coredump, the first thing that you need to do is you need to deprivilege yourself appropriately to make sure that you're sufficiently sandboxed and so on. It's like a big dance that you have to do, and it's still kind of exploitable. We get to that in a second. Yes, we already talked about this. So there's a bunch of problems with this. A couple of them I already mentioned. So privilege level for coredumping process is not under direct user space control. So there is at least a brief period in time where a new process executes with full kernel level privileges. Good attack surface. It's a child of the system work queue, that's what I already mentioned, and not a user space process, and it does not inherit any use source constraints. And here is where the attacks come in, or possibility for attacks also come in. A coredumping process, so a process starts to coredump, can be killed while it dumps core. So it means it's subject to PID's recycling races. That's just a recent bug that we had in systemd-coredump and also in airport. So somebody could SIG kill that process, and if it's fast enough, spawn another process with the same PID, and then systemd-coredump or airport or whatever it is will operate on that recycled process instead of the original process, and can exploit it that way. Every crashing process, if you use the usermode helper, causes the kernel to fork and exec. So there's a lot of overhead, right? So if you have 100 processes crashing, the kernel forks and execs 100 times, needlessly, because you don't have to actually do it this way. But so there is no easy way to elegantly abort a coredump, as the kernel immediately starts dumping the contents into the pipe. So this is probably what I should have said earlier, but essentially the usermode helper is just half of the story. So what the kernel does, it forks systemd-coredump as a usermode helper, and then it hands the kernel the right side end of a pipe, and at a fixed location, standard in this case, for systemd-coredump, it hands it the read side of the pipe, and then the kernel immediately, as soon as the process is spawned, starts dumping all of the memory contents into the pipe. At some point, it will block and wait for userspace to read, and userspace reads that stuff out of the pipe end, and then can do whatever it wants with it. So userspace is actually responsible for writing that coredump out or handing it to another process or whatever. Like it's just a pipe where the kernel stuffs in the coredump, and userspace reads it. So, no easy way to elegantly abort a coredump. What now? So I wanted to get rid of most of the problems, ideally, and so I thought, like, what can we do? We talked about this at great length. Of course, I should also mention, there are additional ways of creating coredump. For example, on Android, this is all done in userspace via signal handlers, which is also works, but it's quite ugly. But it works. But for example, that is one of the few reasons I talked to Jan about this a while ago, Juan from Google. He said why the Sigota process, which is like the process that starts every application on Android, has to have capsysadmin, because it needs to be able to ptrace every process to actually generate the coredump. So you again have like privilege escalation potential in these scenarios. So userspace already mostly does it the right way, I think, or because it already uses a socket to process coredumps and then forward coredumps like in AF Unix sockets. And we're like, well, we could just make this a concept in the kernel itself and like use a socket. And that was the initial first step that we did. So now there's a new mode in the kernel. It's the first of two modes, I should say. There's a new mode in the kernel where you can use this little @ symbol, and this will instruct the kernel to use a socket. So you can specify an absolute path. There are a couple of security requirements that we put on this, like you can't have any dots in there, like you can't have any symlinks in there. The kernel will refuse all of that. And it's pretty easy. The kernel just connects to the socket. Presumably, userspace has already started to listening on this socket, and then it will start to write out the memory contents into this socket. Of the issues with the usermode helper was, as I said, you were subject to PID rate. So. You can hear me? Yeah. Okay. You are subject to PID recycling races. And for the usermode helper, I attacked this problem by essentially introducing a new option. I don't know what the specifier is called, -F or something. And it instructs the kernel to install a PIDFD for the crashing process into the usermode helper, so that right when the usermode helper starts, it always has a stable reference on a process. Quick summary, like a PIDFD is just a file descriptor for a process. It's a unique handle. You can be sure that it won't be recycled, and you know that you immediately notice it when you have been recycled. You get a poll event when the process gets exits or gets reaped, for example. You can't be tricked. The nice thing is, a year ago, 2 years ago, I don't know, we also introduced a concept for AF Unix sockets, which is called SO peer PID. And what it allows you to do is you can, from the socket connection, you can get a PID to the other side of the connection. And SEM PID, which allows you to get the PID of the sender of the specific message. So what you can do if you process a coredump via the coredump socket is like you first get a PID for the other side, for the kernel, and then you also have a stable handle as soon as you connect to the socket. Like the kernel here makes sure there is like a call pidfs coredump. That one makes sure, pidfs register pid, sorry, that one makes sure that when the kernel connects, userspace is able to actually get a PID for the crashing process. And yeah, I should also note, the kernel, like it's literally the process that is crashing, that is writing out its own memory contents, right? It's not like the kernel isn't forking a thread that is then writing out the coredump, the memory contents of another process. It's literally the crashing process that does it. So you get a PID for the crashing process right away. And so this is fairly simple because it's like the same, it's essentially the same mechanism as it's the same thing as the pipe mechanism. Like you have the kernel writes the memory contents and the user space can read the memory contents. So in that regard, it's not that different, except of course there's no fork, there is no exec here. No one is running around with kernel level privileges at any point in time, like because systemd-coredump could just be could fork an unprivileged process that just does actually the processing of the memory contents. So we've taken all of this out of the equation. And then the next logical step was how can we make this even nicer? Because like what I really wanted is to be able to process coredumps on a more fine-grained level. So right now, the only thing that you can do when processing coredumps is you write a string to proc kernel core pattern, and that determines how each coredump is handled, right? You can't parameterize individual coredumps, which is kind of annoying because like sometimes you have massive amounts of memory contents and you want like, oh my god, I don't want this coredump to be generated because like I know this will be like 2 GB or 4 GB. This is like, I don't know, crash my disk or whatever, or this is just uninteresting. I don't care about this process at all. Just skip this. And I introduced a minimal protocol for the coredump socket that allows you to exactly do that kind of thing. So that's a new coredump mode if you use add. I'm really sorry. I wish I could give you a better API, but because for legacy reasons, we have all collectively apparently decided that writing into a proc file is the future of Linux API development. Honestly, it's just a legacy thing. It would probably be a better way of doing it in the future. I would really like to move away from configuring such APIs through procfs. But in any way, it's a simple protocol, request-response protocol. When you use this mode, the kernel will not just write the memory contents into the socket, it will send you a coredump request message, which is just a struct with a specific size, which is the first member, and the kernel will tell you what features it supports to process this individual coredump, and it's extensible. So what userspace can do, it like can peak the size for it. You can do this in a couple of ways, but the way I wrote the POC is essentially userspace can peak the size of the struct, and then read the request struct out that the kernel had, just the size that it knows about, discards the rest of the size, and then it can look in the coredump request struct, first of all, what the size of the expected coredump response is, like the ACK, what the supported features are, which is like here in the set in the mask, and you can see above there is coredump kernel, coredump user space, coredump reject, and coredump wait. I'll get to that in a second. And yeah, the kernel supports currently coredump kernel, which is the kernel actually writes the coredump for you, meaning it writes the contents of the coredump into the socket. Coredump user space means that the kernel won't write anything. For example, you can generate your own coredumps, like that's possible in user space. Just relying on procfs, you could generate your own valid coredumps if you wanted to. That's how gcore, for example, works from GDB and a bunch of others. So if you just wanted to do it in user space and you just want to be notified that something crashed by the kernel, that's a way to do it. Coredump reject, what it says on the tin, if you raise coredump reject in the response, then the kernel will just skip that coredump completely. It will not write anything, it will not do anything, it will just abort the coredump. And coredump wait is quite important because, I forgot to mention this little word. By default, I think most distros enable this, of course, but by default, the kernel will not, for user space, to have finished processing the coredump. So the kernel will, like for example, if the process is small enough that crashes, the kernel will write out the coredump into the socket and then just exit the process right away, which again makes you vulnerable to pit recycling races and so on. And you can instruct the kernel, which most of the like appert and systemd-coredump do, you can instruct the kernel to wait to block the process from exiting until user space has actually finished generating the coredump. And coredump wait allows you to do that as well, like instruct the kernel to wait with exiting the process until you actually finish generating the coredump. In user space. So user space is expected to respond with a coredump ACK, and the coredump ACK works exactly the same way like the coredump request. You set the size of the coredump ACK, the kernel, because the kernel will always tell you what size of the coredump ACK it supports. It will expect you to always respond with that size, and then you can raise the options that you want: coredump kernel, coredump user space, reject, wait, and so on, and then the kernel will start writing the coredump. If for whatever reason this thing is invalid, like you raise invalid options or whatever, the kernel will write a reason in the form of a 32 byte integer coredump mark regegg. You see this enum here, and it will exactly tell you why the coredump request fails. So this is pretty trivial. It's not trivial, but I mean it's a pretty easy response ACK protocol, and it's extensible. One of the things that I, for example, thought about, we talked about the coredump filter before. When you have a really large process with massive memory contents, you might want to skip some pages or a bunch of pages or memory contents, and currently you need to pre-configure this when you start the process. We can easily just move this into this request response protocol so that you can tell the kernel, for this specific process, I want you to skip a bunch of the pages. It's not necessary for you to do this. So anyway, this is pretty simple. I think I've written an implementation of a coredump server for this, and systemd will switch to this as well. That's at least I've spoken with Leonard about this in great detail. So in the future, this is hopefully the protocol that systemd will be using as well. So are there any problems? I'm sure we'll figure out some problems with this API too. That's usually how it goes with these things, but there are a few advantages. So there's no more processes that are running around with kernel level privileges. You don't need to fork an exec. Obviously, you can parallelize coredump handling as much as you want in user space. You know, you can even rate limit it by using the what is it, like the socket backlog limit, for example. You can abort coredumps before the kernel does anything at all. Again, this is currently not easily possible. It's extensible in the future. This is something we should probably talk about. Coredump handling for containers, even with this API, currently remains a task for user space itself. So the way it currently works is if you have a process that coredumps into container, the request ends up in the initial set of namespaces, right? So it's not in any way delegated to the container because it's not actually clear what that would mean. So, for example, if you use the mode where the kernel writes to disk, it will always treat it relative to the initial mount namespace. Let's make it easy. To the initial mount namespace, so it always will end up in the host's hands, the coredump, which I can see is like annoying, because if you have a process crashing in the container, you might want it to be able to be accessed in the container. Systemd has like a solution to this where it forwards the coredump into the container, and I think Upward does the same thing as well. And there were people who tried to convince me that we somehow namespaced this. Like with the socket, you could do it, because IF Unix sockets are bound to, they're just paths. You can easily probably namespace this somehow. But that would also mean that systemd on the host wouldn't see all coredumps anymore, which is not ideal. It would be a pretty big switch away from the current model. So my preference currently is still that userspace is responsible for forwarding the coredumps to the individual containers. Like, you can have multiple solutions to this. Like, you could have a socket in the container that the containers know where to listen on for coredumps. And then systemd coredump in the container, or apport in the container, whatever runs in the container, can just like take the coredump from the socket, or systemd just like places it at a specific location inside of the container, and then you can get access to it. So again, this is like a user space problem in my current thinking, at least. Make good arguments for why we should namespace it and how we can do so safely, then we can probably revisit this. But yeah, I think that's all that I had on this, and I'm excited for questions. Yes, Joseph?
So I actually have a good argument for namespacing it, unfortunately. I'm thinking of cases where we have trusted and untrusted containers on the same machine. And in the case of trusted, we have from my previous job, user data that we don't want exposed outside of the like more locked down container. And so having the core dumping happen there, where only the container that is trusted, that has all the encryption, that has all the things, have access to the user space, processes, memory, would allow us to continue to make sure that I say us, them now, all of that memory is contained within the secure environment and not exposed to the host.
Wouldn't the host always have their higher privileges, as you said? With confidential computing, right? But then you have a hypervisor as well in there somewhere? Depends. Sorry. Sorry, another comment that when we talk about this is that works if you have containers that remain after they crash. If it's a single process container and it crashes, there's nothing.
So I'm thinking more for like crash statistics. Like, obviously, like, we don't care about the contents themselves. We want to make sure the contents of memory stay secure, but we want to, like, say this process crashed in this location, and so call that out, and then the process, like the container, gets destroyed at that point, and everything, like the destruction part is permanent. Right?
I have a question regarding the extensibility of the protocol that you have described.
Right.
I'm not too deep into the whole kernel development scene, but my understanding is that the ABI of the kernel itself is not guaranteed to be stable. Like, which guarantees are with that protocol, and how would you, like, is it versioned, or how would a user space program determine and to what type of protocol it's talking if it gets extended in the future?
So I think there are two different things here. The first is we have a kernel internal API and ABI, and that one isn't stable. So that's things like between modules, or like internal helpers and so on. That's a totally separate issue. And then we have the UAPI, all that stuff that is exposed to user space, and that is guaranteed to either be stable or be extensible in a backward compatible way. The kernel has a concept of, for a longer time now, struct versioning by size. So all of the structs that, not all of the structs, all of the, for example, newer system calls that take more than basic flag parameters usually have a struct, and alongside the struct, either as a member within the struct or as a separate argument to the system call, have a size, and all of the structs are 64-bit aligned. So if you add a new member, for example, then the size will necessarily change, and userspace will then specify the size of the struct that it knows about, like for example, and then if the kernel sees that, oh, this is a user space that is older than what I have, it will restrict itself to the features that userspace knows about, and if the kernel sees it sends me a larger struct, then the kernel will enforce the requirement that all of the additional fields it doesn't know about are zeroed, like the memory is 0, and that's how you get forward and backward extensibility. So that we've used that quite extensively over the years, and it holds up. And this is sort of similar, only that here you pass, so the coredump request struct, as an example, it has this size parameter, and that is the size of the whole coredump request struct. So the kernel sends to user space like, hey, this is the size of the whole coredump request, and let's assume we have grown this struct, and then user space sees like, is it knows the size of the struct it knows about, and then it knows, okay, the kernel struct is larger. I need to kind of annoying. I just need to write the bytes that I know about and discard all of the additional bytes. So that's how you can extend it. If you have, yeah, so that's the basic model, and it's the same way for the kernel ACK. Only here it's a because the old user space is of the ACK request is that it expects it will tolerate, how did I do this? I described it here. The size member must be set to the size of struct coredump ACK. It may never exceed what the kernel returned in coredump. User space like knows that technically I can work with kernel that have new features that I don't know about. That's the ACK request that you're going to send. The thing is, like, this is for low-level user space, obviously. Like, it's not an API or a protocol that like you should implement in a bash script, right? That's not the idea here. I mean, you can do this, like not with this protocol, but if you wanted to process coredumps now, you could use socket. I did this. Like, you can write in a path to a socket.
You shouldn't, but
you shouldn't. But I did. This is what I did for testing, and then use socket. Listen on this, and then like the kernel writes you the coredump into the socket. So it's actually made it way easier. You don't need a user mode helper for this anymore. But anyway, so that's the forward-backward compatibility here. So that is guaranteed to be stable. It's 64-bit aligned, and trust me, it works.
Any other questions or comments? So who's going to send a pull request for systemd-coredump? Oh, we have a volunteer.
So by 64-bit aligned, do you really mean rounded up to 64 bits? Because align by itself wouldn't mean much, no?
Yeah, padded to 64 bits. You always grow the struct by 64 bits. So if you just wanted to add like for example here you see it, that's usually what the kernel does in all its structs. Here you have the U32, which is the size, because that's all you need for a size, unless you want to have a 64-bit sized struct that you want to send the kernel. Good luck. And the spare is just there for padding. Like you can already use this member, and then you have the 64-bit mask, and when you introduce a new member, you also use a new 64-bit member. That's how struct mount adder works. That's how the struct's extensibility is done this way. Now, of course, we're all going to be in deep shit if we ever decide to have a 128-bit kernel, but then, you know.
He has a 120-bit kernel.
Yes. The kernel developer doesn't know how we enforce this. Like, so you said this, and this is news to me. And I would definitely add a 32-bit field, not realizing I'm supposed to pad to 64 bits. Do we have anything in place to make sure we?
Yes. So it would give you it would compile time yell at you.
Okay, so there's a compile time.
Yeah, we do this for all the. There is no uniform thing. Like for every struct that we have, like we have a build bug on, and that checks like that's
all right,
for bit aligned and so on. And then you can see here, for example, there's also always the current version that the kernel knows, like coredump sock x size version 0, and then we assert on that.
Other questions? Yes.
Is this available in Linux release already?
Sorry?
Is this available in Linux release already?
Yes, the 6.15, I think. 6.15 and 6.16, I'm pretty sure. Yeah. And if not, it's 6.7. But definitely released. Let's put it like this. I can't remember. I'm sorry. I can't remember all of the stuff.
You did this a few months ago, so I think it's 16 for sure.
Yeah, but in the kernel we have like reliable release cycles.
Rude. Any other questions?
So I really hope that this is not even necessarily protocol, but I hope like in the future, like at least the basic socket protocol will be what replaces all of the user mode helper stuff. Like at some point I would like to get rid of this user mode helper concept in the kernel completely, because it's a pretty backwards concept.
Are there any other left apart from coredump?
Yeah, I think if you do request module, I think that's a user mode helper. Like if you load modules, I think in some scenarios user mode helpers are involved, but I don't remember the details anymore. I know that BPF filter or BPF tool or something like this was premised on this.
So do you have your preferred way how to handle coredumps in containers? Like if you could choose one that you think is the best, what would
No, I mean, for containers, coredump handling is obviously, it's not great, right? Because like, as I said, if you have a coredump in the container, it always ends up in the host. My preferred way currently would be that you do the forwarding via systemd. Preferably, we could also just have a socket, a well-known socket in the container, the same way we have, let's put it this way. You could easily fully emulate namespacing, right? Because when you start a container, like let's say systemd starts a container, like we discussed, either via nspawn or the systemd executor, it could also set up the same path, just namespaced inside of the container that is written in proc sys kernel core pattern, and then systemd-coredump inside of the container, if it wanted to, could just start listening on the socket. And it's not the kernel that is writing the coredump contents into that socket, but it's systemd that is forwarding the coredump that it gets in the initial namespace into the container. And then it's completely transparent, like systemd-coredump behavior in the kernel, in the container, is exactly the same as systemd-coredump on the host.
Yeah, this is sort of like how it works now, I think. But the thing is that what about the containers which don't have systemd inside? This is the problem that I was dealing with, like sort of these app containers, not system containers.
Sure, but I think that's a good point that Luca raised. First of all, if you have an application container that just has a process, presumably the only process that crashes is the application container process. So it's pretty useless if you have it inside of the container. If you have like a couple of processes in there, yeah, I don't know. But what would it get you if the kernel? What would it get you if the kernel had a namespaced way of doing this and nobody was listening on the coredump socket inside of the container? Sure, I mean, you could argue that you namespace it in a completely not insane way, but you could namespace it in a way that you say, on a host, you can write into proc sys kernel call pattern and use the coredump socket, and then in a container, you can instruct the kernel to write it into a file inside of the container, which I think is just seems pretty wild to me.
The way I see it, like if you want to process the coredump inside of the container, then this implies you have to have a service manager, right? Like, because there needs to be something inside of it, so you need two processes, right? The payload and the coredump processor. But so if we now have established that you need a service manager, then yeah, either it's a systemd, then everything's clear, or it's something else, right? So let's just say Docker-style containers should never have that issue because they're kind of designed with not having an system.
I mean, you could still make this work transparently. I think I mentioned this before, not transparently, but you can make this. You could still make this work by saying for application containers that want to have access to their coredumps. Let's say they have like 2 or 3 processes running. You don't forward it on the socket. You just place it into a well-known location inside of the container. When you start up, you basically say, tell me what location I should dump your coredumps, and if they're not super sensitive or something, then I just forward them to you and place them at this location. If you want to look at them, look at them. Then you don't need to have a service running inside of a container. That's also an option.
Right, that's all the time we have. So let's thank Christian again. Thank you.
Thanks.